Welcome back everyone. An update on RoverBot. We've made a fair bit of progress since the last video. From memory, the last video was me going through the CAD design that I put together in about a week. And I've made some changes to that, but also made significant progress, so I wanted to take you through it. The big update, I suppose, has been turning this into an integration test. So I managed to get my hands on a 3D printer, learn how to use it, and I've been fabricating or 3D printing the parts that I need just to test a corner of the rover. So my goal was to kind of get the entire geometry set up and the mechanical parts set up for actuating a corner. And so for me that means one motor, one servo, the bell crank mechanism, having all of that sort of stiff enough and rigid enough that it will perform within tolerances for testing. And so that's been a big part of what I've been working on, and then also starting to integrate the firmware into that. So the integration is mechanical, electronics obviously, and then the software to drive all of that. So I wanted to give you an update today, and let's have a look at it. So this is where we're at now. This is what the beginning of the rover is looking like. It's pretty exciting. I've managed to build the entire chassis. It's a 400mm long chassis, and the cross members that create a fork into the kingpin, into the motor housing upright, whatever we're going to call that, to a test wheel. So I've integrated the electric motor, I've coupled that to an axle, the axle is connected via a hub to the wheel, and then I've also been able to link everything around the bell crank. So I have my bell crank and idle link here, my steering rod, the tie rod that connects me to the steering arm. There's been a lot of learnings through this process, and then I've just printed a temporary part here. This will actually be a ball link push rod, a ball link on either side and a push rod. I've 3D printed a part to connect the servo horn to the mechanism. Now the servo itself I've been able to mount in a custom mount or bracket that I've designed and built, and I've actually turned that into a single unified piece that mounts the main pivot points here for the bell crank steering mechanism bolted through the chassis right underneath here, which you probably can't very well see. Plus I also have some additional support here just in case. There's actually 0.5 millimeter of gap there so that it doesn't rub. But if there is some wobble, which there currently is, and I'm not terribly happy about the amount of wobble here, part of it is ball link, but part of it is also just the give in the material that I'm using. I've used PETG-HF, but ultimately this will be aluminium machine parts. So it's looking pretty darn good to me. So that's the mechanical piece. The aluminium tube I just sourced from a hardware store in Australia called Bunnings. It's just a 40 by 20mm aluminium tube. It's a 2mm wall. It's pretty soft. I have these sort of what I call crush tubes here to prevent crushing. That is just PETG again, so it's not very strong, and that would be aluminium in the long run, or potentially it would be a fully customized chassis. So that's working for now though, and it gives me stiffness across the chassis. And then combined with M5 hardware, I've got different hardware, M5, M4 and M3 around the place. That is working out quite nicely. So that's where we're at with the mechanical side. Now, the servo bracket I just designed yesterday, that holds the servo in exactly the right position for center. Well, basically it's all calibrated, and I've measured that out. And it reflects CAD exactly, which was quite nice. And I found the manufacturer's 3D model for the servo, so I was able to design the bracket with very, very tight tolerances to hold it, and it's really beautiful. It's snug, and I haven't even put screws in it yet, and I will obviously, but that's currently really stable. It is a 30 kg/centimeter servo, so it can generate a lot of torque, so the stability there is important. Now I have the servo connected into the bus adapter, the bus servo adapter if you remember, excuse the birds outside, and then that's connected through to my ESP32, which is over here, and then I've got a RoboClaw currently just operating in like duty mode, I guess you'd call it. There's no feedback from the motor, I'm just driving positive and negative to the motor. I have These motors do have encoders. I do intend to use them. I haven't set that up right now. The firmware doesn't know about that anyway. And so this is the current setup that I talked about last time. It's all being driven from my laptop here, which has decided to go to sleep, and nothing's really changed there. I haven't done a lot of work on the firmware since the last time, but you can kind of see if I get out of the way of the shadows and the reflections, you know, this is startup. It just, I've done some work to improve constraints and safety around the way that actuation happens. And I have things like arm disarm, and I have like safety stop. So if there's certain events like I lose a motor or I can't talk to a controller, then I stop the whole system. So that's all been implemented in firmware, and I've done some work there. And I'm just doing this all off the bench supply. And so what I wanted to do was maybe just give you a quick demo, because what I've rustled up is a test script that uses my wacky, very temporary UDP protocol to basically just sort of put the rig through its paces. And so if I kick that off, let's see what happens. So it'll just go into a centered position immediately, and then it will start to cycle through different commands where, you know, it's just moving the motors slowly here. It started with a 10,000 duty cycle, it's gone to 20,000, it'll go to 30,000, and so on. And then it will start to do steering tests and basically make sure that the steering angles that I've set up and the way that I've calibrated the system works appropriately and doesn't go past mechanical limits that I care about. And so we can just watch the system at work here. Now, nothing's really changed here as far as I've connected the laptop over USB-C into the ESP32, whoops, just for serial for now. But the communication that's happening here from my test script is just using the Python command line driver, if you like, that I built that just talks UDP over the RoverBot's network. So the RoverBot hosts its own little wireless access point, and then the laptop joins that and just sends these commands over Wi-Fi to the ESP32 and sends UDP commands. And so that's it. That just ran through a set of different commands, and it's been successful, and it's disarmed at the end. So you can see how that all works. So that's where we're at currently. I'm pretty happy with the progress. I have stalled a few times on just getting the right parts. Getting this push rod is proving a little bit more troublesome than I would like. And there's obviously work to do here in terms of improving the mechanical design. I have discovered some pretty significant mechanical issues here though. So maybe I'll close out the video with that. But before I do, the next steps here are really to go and build out the four corners and hopefully in the next update video just have everything configured and working. There's a lot more firmware work to do, but currently the firmware is sufficiently robust that it can run through this sort of a test harness like this. But the next video should have all four corners built. I probably won't have the hardware. It'll still look pretty messy here. So that's the mechanical build that's going to happen next. I'm happy with the geometry largely for this version, and I'll get into that in a second. And then the next big thing on the critical path is getting the custom PCBs done. And so I've made a lot of progress on the custom PCBs, and you know, I haven't taken you through the schematic for the power board here, but there's a ton of stuff that I can talk about on the electronics side, but I haven't yet. I'm connecting controllers. So really it's printing, it's doing the two custom PCBs, one for power and one for control, where the ESP32 and an IMU and other things will sit, and then getting the power management configured properly and tested. So that's probably on the critical path is PCB manufacture. And then beyond that, it's just revving the firmware over what I have right now. So the firmware needs to have a kinematic model of the rover. There are different models depending on the type of steering that I'm going to use. For example, at the start, I'm going to have probably reverse phase steering. So, you know, if the steering at the front is turning to the right, then the steering at the back will turn to the left. Okay. I'd like to have a mode where I can do crab steering, I think it's called, where the wheels stay parallel. But I want to set this up to have the right Ackermann geometry, and so that will cause a little bit of a conflict with crab steering, if I understand things correctly, because Ackermann geometry means that, you know, your two front wheels steer at slightly different angles, to take into account that they're tracing different arcs, and so that obviously conflicts with what I want to do with crab steering. But at least I'll have reverse phase, and then I'll also be able to do probably just disable steering at the back and just do front steering, because the Ackermann geometry should still work there. So at the very least, I'll have at least two kinematic models for how the rover steers and moves around, and I'll start with the reverse phase to get the tightest angles I can. I did some calculations here. With the geometry that I've built out, I think the maximum steering angle I can realistically expect is probably about 25 degrees, which is not really what I wanted. I wanted to get it upwards of 30 to 35 degrees. But for that to happen, I need to really reduce the distance between the kingpin and the steering arm here. Currently that's about 50 millimeters just because it sits around the motor volume here. And so I will be looking at redesigning this. But that's it, right? So get all four corners done, get the PCB printing underway. I've done layout, and I'm sort of finalizing routing on the power board right now. And so there's work ahead there, and then improve the firmware with kinematic models so that it understands how to actuate the rover in a consistent, sane way. Now, the final bit I want to talk about here. There's been a lot of learnings where I'm going to have to redesign the corner quite significantly. So through the process of doing this, not only things like the steering angle and the distance between the kingpin and steering arm, but what's called the scrub radius. Okay, now when I first designed this, I wasn't going to have a separate axle on the machine. I was going to just have direct drive off the motor. And in thinking about that, I didn't want to introduce forces on the motor rotor itself, knowing that there probably isn't any good bearing support in there. And I don't intend to take this off-road, obviously. It's going to be more of a, trying to do research with this little vehicle. But I ended up introducing an axle for the wheel. And so that meant adding two bearings and a coupling between that and the motor shaft. And that was all fun to design and engineer, and that's working quite nicely. But what it's introduced, let me just show you, what it's introduced down here is basically an additional, at least, so the axle comes to about here, okay, and that's the coupling. And then from there, that's where the motor shaft begins. So I originally was planning to have the wheel about here, and the scrub radius would have been manageable. It still would have been about 30 millimeters, but it would have just been sitting around here. Now I've added 50 millimeters, probably thereabouts, to the scrub radius. So I now have a whopping 80 millimeter scrub radius on this design, which is really terrible for repeated, accurate movement. And when I'm trying to do classic odometry, I'm using encoders, and I know exactly how far the servo has turned, and I know exactly what the motors are doing through the encoder feedback into the system. I should have really good, accurate information about what the rover has done and where it is. But the scrub radius introduces additional skidding as the system turns, and that's just physics, and I can't control what happens in the real world. But without the ability to get feedback and measure that, it's going to introduce error. And so I'm going to forge ahead with this design and just start to benchmark with like an ideal kinematic model where the scrub radius is close to zero, what I would expect the system to do versus what this system will actually do. And that'll be quite fun in its own right, just to understand how much error this introduces. It's just, I guess, an artifact of iterative design where I wanted to start here and then I started to add things to solve other problems, and I ended up with another unforeseen consequence, at least unforeseen with my level of experience. So that's where we're at with the scrub radius. The other significant thing that I didn't think through very well is the kingpin itself isn't isn't retained axially. Okay, so I've relied on a clamping force to hold the fork and the upright together. Okay, there's no axial retention here. If I really try, I could pull this fork off if I apply enough force. Now, as the machine moves around and as I add more weight to the actual chassis, the forces here could slowly walk this off or move around, and that's not great. So I originally thought, well, let's just extend the kingpin and do something like a collar and retain it that way. Well, firstly, collars don't really clamp very well to, this is a clamping collar. It's a good quality one, but it doesn't clamp to PETG or printed material. It would probably clamp to aluminium or steel quite nicely, and this might help solve the issue. But it does add height, and I don't have a lot of clearance under this machine as it is. And yes, I could go with 120mm wheels rather than 96mm wheels, but I don't really want to start to just, it feels hacky to solve it this way. So given that I also need to somehow, I can probably shrink the width somewhat, but I'm going to have to move the kingpin right out here. And if you squint at this really hard, it sort of looks a little bit like a double wishbone. I mean, I don't have wishbones here, it's just one piece. But a double wishbone design kind of does come out like this and tapers. And I didn't design it that way because I wasn't even really familiar with a double wishbone design until I started doing this. But I will come up with some design where I can bring the fork or the wishbone or whatever it turns out to be as close to the hub as possible so that I end up with something like a 10mm scrub radius rather than an 80mm one, which gives me much more predictable movement and steering and hopefully less error as I'm moving around. And so that's the opportunity, I think, then to redesign the kingpin and build it in such a way that it's captured axially in a much more robust way. And I have some ideas for what I want to do there and how to design that. And it will probably be a custom shoulder bolt in steel with a threaded end that I can, it's an M5 or an M6, it's a 6mm, so M6 thread and screw, nut rather, that clamps down and does that top and bottom. And that will add, 5mm on either side or so, but I can capture the head of that inside the motor housing. And anyway, there's a whole idea there and design. So that's where we're at. I will forge ahead with this design. I will get it to a point where I can benchmark it against an ideal kind of model, and then we can redesign this whole front end piece, which will be fun in its own right. All the more reason to have basically ended up getting myself a 3D printer so that I didn't need to go through the expense of CNCing any of this until I knew what I was doing. And so that's where we're at, folks. A bit longer video again as usual, but worth an update. I thought it's been 2.5, 3 weeks since the last one, and really happy with how this is kind of turning out, I suppose. The mechanical side of it is stronger and more robust than I thought it would be, even with the PETG material. I've used some basic PLA, but I've used PETG-HF in most cases, and just generally I think it's working out quite well. So next video for me should be all 4 corners built out, the electronics kind of completed, and then some additional firmware improvements to start understanding what the kinematic model for this looks like and start controlling in a reverse phase manner, steering at front and rear. And that will then lead into odometry using the encoders, and then that will lead into other more exciting experiments. So stay tuned, folks. Thanks for hanging in there, and hope you're enjoying the updates. Comment below if you want to give me some advice or you have some ideas or it's exciting you and you're doing something similar. And like the video and subscribe, please. It'd be great. Cheers.